Yes. So once again, thank you very much, Wim, for being here to talk about the case of overusing proportionality. I think many of us here know Wim or his work. He works at the Catholic University of Leuven on mathematics education, and I'd like to give the floor to him immediately, actually. So it's yours.
Well, thank you, and thank you for attending this seminar. Indeed, there seem to be many people. I would have loved to come to Utrecht to give this seminar, but this will do, I think. When I got the invitation, I started thinking, what should I talk about? And the main message I want to bring is that looking at various obstacles in mathematical reasoning can shed a lot of light on how mathematical thinking and learning happens. And I will use one of the cases, one of the lines of research that run already for quite a while in our research center, which is the overuse of proportionality. So basically, I will be looking at about 20 years of research, and I quickly counted, indeed, I will be roughly discussing about 20 studies as well in a short time. So please forgive me for being not being too detailed in some of the studies. Sometimes I will talk about the method, but most of the time I will talk about results, mostly an interpretation of results. Okay, I thought it was a good idea to start here. Concluding thoughts. Some of you may go offline, may fall asleep, may get bored. Whatever, so already some of my concluding thoughts, so you know that you have an idea on where I'm going to. The main message I will want to give, and this will be also one of my last slides, is that I think errors will be a kind of microcosm where you can investigate mathematical thinking and learning. And then more importantly, to do that well, you need to be at the same time a mathematician, a historian, a teacher, a sociologist, and a cognitive and developmental psychologist. So I will try to show you that you need all those perspectives and even more perspectives in order to understand very well what happens. But I will try to clarify that in the coming 45 minutes. But before doing so, there are already the terms and conditions that if you attend this session, you may be recorded, but I have my own terms and conditions as well. So by attending the session, there are a few other things that you need to accept. You won't have to tick the box, but I want you to accept that I'm neither of the preceding roles. I'm not a mathematician, I dare to confess that. I'm not a teacher, at least a mathematics teacher. I have a teaching degree, but not in mathematics. I'm not a historian. I'm not a cognitive developmental psychologist. I'm an educational scientist. So already a disclaimer here, if I tell historical nonsense, this is because I'm not a historian. Please forgive me. Second thing is, I will repeat myself. And that's quite important as well. I do that for a very good reason, for a didactical reason. You will see the same examples, the same mistakes coming back again and again. And each time I will try to shed a light on the example from a new perspective, with a new explanation, with new evidence. So examples will come back again and again. Third, that is, almost all the time will be spent, or we will devote to learners making errors. And that is not because I think learners are stupid, that they're not able to do mathematics, etc. It's also not that I want to be pessimistic, but I think that when students make an error, we can learn a lot from that. Also, the learners can learn a lot from that. The analogy I want to make is with, of course, I'm a Belgian, so beer for us is an important thing. And some pessimists will say here the glass is half empty. Optimists will say it's half full, but a Belgian just simply says, there is room for more beer in the glass, and this is the perspective that we will be taking. So there is room for improvement at many places when children make errors. And the fourth thing that I want to say is that I will repeat myself for good didactical reasons. Okay, now to start with looking at errors, I will start with a few examples with very little explanation, but the explanation will come throughout my talk. First example, and many of us, of the people I know in Utrecht, know this example already, which is a very simple word problem. Ellen and Kim are running around the track. They were equally fast, but Ellen started later. And when Ellen has run 5 laps, Kim has run 15 laps. When Ellen has run 30 laps, how many has Kim run? Now, this is a problem that's quite simple, in fact, because they run equally fast and one started later. So the distance between both girls here is 10 laps. So 40 laps would be the right answer. But you see, this is an older study that we see, but we see it also in newer studies, that the performance decreases on this problem. So students do worse from 3rd grade, think of 8, 9-year-olds, to 6th grade, to 11, 12-year-olds. So performance decreases. Okay, I'll explain later why that might happen. Another example, a probability problem. The probability to get at least 3 heads in 5 coin tosses as compared to the probability to get at least 300 heads in 500 coin tosses. Well, many people tend to think that both probabilities are equal to each other. You see here some evidence that we obtained in 16-year-olds. We also know that most educated adults think the same way. Just an example. Physics then. A girl is standing on top of a tall tower and she releases a little rock. After a second, it's traveled 5 meters. After 3 seconds, how long of a distance has it traveled? If it hasn't reached the ground, of course. And so many 11th graders who know the physics behind this will answer 15 meters. This is something we investigated as well. Okay, now how to explain those problems? Well, many people will have noticed that in all those cases, students are using proportional, or some others call it linear reasoning. In simple words, many people express it like that: k times a, k times b. If the time is 3 times as much, the distance is 3 times as much. Or they use those arrow schemes that you can see here. So if 10 eggs weigh 80 grams, how much, if 10 eggs weigh 600 grams, how much do 80 eggs weigh? Well, it's 8 times more eggs, so 8 times more weight. So all those are applications of a very simple linear function. Now, is this an explanation? I would say no, it's just a good description of the error that students make. It's not an explanation yet. Now, an explanation might be, and I enjoyed to include a citation of Freudenthal here, is that students are overusing linearity because it is what Freudenthal said, a suggestive property of relations. So people are, as he called it, seduced to deal with relations as if they are linear. Now, of course, that was a statement, a quite blunt statement, but there isn't much evidence yet that this is true, and definitely not when Freudenthal used it. It was his insight, but let's look what the evidence is, whether that seduction character is really there or whether more is going on. And I will explain that this sometimes is the case, but more is going on, definitely. Okay, before going into the explanations, again, a disclaimer. I will be showing you situations where a linear relation might be applicable or not, and sometimes it's really a matter of adequate mathematical modeling. And so, yeah, you can debate whether linear relations are at stake or not at stake. Just a simple case is this one. I actually don't know in this case whether 2 balls of yarn are twice the fun as 1 ball of yarn. I have no idea. Cats apparently know it's twice as fun. You can't see it from the expression of Garfield, but he's having fun, apparently. The concept of the talk is like this. I will look with you at explanations for the kinds of mistakes that we've just seen. I will show you new mistakes as well. And we will show that explanations can be found in the mathematical concepts that are involved, but also in the educational setting, in the way our mind works, and in the way our mind develops. And the concept is so that I will always start with a very simple explanation. For instance, in mathematics, a simple, straightforward idea that many people have. That's the reason for the mistake. But then I will come with a better explanation within mathematics that's more subtle, more fine-grained, more theoretical. And the same for education, for mind, for development. So the most straightforward idea is, students make that mistake because they lack in mathematical knowledge. They don't know how to do the problem, or they have learned the wrong mathematics, for instance. Okay. There is something going on, of course. I showed you this probability problem already. And indeed, if you want to calculate the probability to get at least 3 heads in 5 coin tosses, that's difficult. It's even more difficult to do it for 300 heads in 500 coin tosses. It's very difficult to calculate that. Or alternatively, if you would need to understand the law of large numbers stating that you expect an outcome closer to the mean, the average here, in larger samples, more likely than in smaller samples, that's a very complex understanding. So yes, this may play a role. Similarly, many mathematicians in the past have made mathematical mistakes. Cardano is one of them. He developed quite some insights into algebra, but he made some substantial mistakes in probability, and he was a gambler, so he suffered quite a lot financially speaking there. For instance, he thought that you have a 50% on rolling 2 sixes if you roll the dice at least 18 times, because 18 times the chance of 1/36 for 2 sixes in one trial gives you that 50%. But that is wrong. If you want to know why it is wrong, we can go into that in the questions. But so many famous mathematicians have made mistakes here. Okay, physics. I showed you this example already as well. It is quite difficult to understand the increase of speed of a falling object. Although the students here have learned about it, they applied a straightforward linear function. But again, in the past, many people have made that mistake. Think of Aristotle. He thought in the same way as these students thought. He thought that bodies fall at a constant speed and that the falling speed is proportional to the weight of an object. So if it is twice as heavy, it is twice as fast. And it took until Galileo, I think, until they discovered that objects do not fall at a constant speed and that falling speed is not related to the weight of an object. But of course, what could Aristotle do? He could only base his theories on either experience, but it's very hard to judge speeds, for instance, especially if you don't have measurements. That's really difficult. So the best theory that he could come up with was one wherein, for instance, the weight is proportional to the falling speed and that objects fall at a constant speed. Okay, now what we saw is one explanation, but what we saw is also not sufficient. So the explanation that students do not understand the mathematics sufficiently cannot explain why linear errors are committed. Why do students recur to linear functions? So we need to look at a better explanation, which can be situated in the mathematical concepts themselves. For instance, we talked about probability already. Probability and proportions have a lot in common. And Fishbein already wrote that the intuition of relative frequency is involved in proportion. So at a basic intuitive level, he says the two schemata of probability and proportion share the same intuition. And that comes very clearly forward if you say there are 2 boxes and you need to draw a white ball in one of the 2 boxes. Well, the probability of drawing a white ball is the same in 2 boxes because 2 out of 5 is the same as 4 out of 10. So that's a scheme that is very relevant in probabilistic reasoning, and thus proportional reasoning is involved. And so the problem that I showed you before is very similar. It comes really close. 3 out of 5 and 300 out of 500 attempts being successful is a quite similar scheme, but in this case, the proportional scheme doesn't work. Area is another domain where students struggle with proportional reasoning. It is a 2-dimensional concept, but it is often treated as a 1-dimensional concept in reality. We worked a lot in past research with this problem. If you draw a Santa Claus, let's say of 50 centimeters, and then you want to draw it again 100 centimeters high, and for the smaller one you needed 6 milliliters of paint. How much do you need for the larger one? Well, we found many students reasoning that it's twice as high and twice as wide, so everything is doubled. So also the area is doubled, also the milliliters of paint you need, a 1-dimensional concept, milliliters of paint, is doubled as well. So our idea of area is often a 1-dimensional one, especially if we turn to painting something, for instance, which is a one-dimensional concept in itself. And so again, Freudenthal already wrote about that, talked about how linear enlargement is something that is not treated well, mostly in education, where the focus is very often about formulas, while the fundamental behavior of linear enlargement is not really studied in education. Okay, so far we had mathematical explanations, but those shortcomings in the mathematical knowledge and the mathematical subject matter or the concepts involved cannot explain why students would go to more complex solution methods in simple problems, or why there is an increase with age of mistakes. And yes, I'm referring to this problem that I showed you in the beginning. You see the light blue or almost white bars on the screen, that the number of correct answers decreases, and the explanation is that more and more students give proportional answers, thinking that one girl has 3 times as many laps as the other girl, and this ratio should be maintained, so they answer 90 laps. You see that this happens quite often in 6th, 7th graders. It's not yet present in 3rd grade. It decreases again 8th, 9th, and so on grade, but adults make the mistakes as well. And so we don't have an explanation for that. So let's try to explain that. And there we should look at education. I don't know if that's the best word possible, but the teaching approach, didactical approach, might be a straightforward victim, like an explanation to look at. And indeed, if you look at education, at some times in students' primary and secondary education, there's a lot of attention to proportional reasoning. It is a major focus at certain moments, and students meet a lot of applications, both in mathematics and in physics and in chemistry, etc., because proportional reasoning is important. So I would say this is unavoidable. You have to do these things. And this explains why we see, for instance, this is a proportional problem. 4 packs of pencils cost €8. If you want to buy 24 packs, how much do you have to pay? Well, 6 times as much. You see that quite some 3rd graders are already good at this, but performance increases very fast where the teaching of proportionality happens, which is 4th, 5th, 6th grade. But this development goes very well in parallel with the increase of incorrect proportional answers to this additive problem. So when students learn proportionality, they apply it immediately also in additive situations, apparently. So there are some things that are unavoidable. I already explained proportionality is important, but some other things are avoidable and could be done differently. One of them is discrimination training never occurs. It seems, and we scrutinized textbooks for that, we did a textbook study, and we rarely found textbooks wherein students learn to distinguish proportional from non-proportional situations. Typically, the whole series of problems has to be solved in the same way. And what we also see is that using superficial cues is most of the time successful. For instance, if students meet a missing value word problem, they can almost always be solved by means of a proportion. And by a missing value problem, you could mean these problems. These are word problems where 3 numbers are given and the 4th one has to be found. And students then reason, oh, in this case, there's a square lawn with sides of 200 meters, another square lawn with sides of 600 meters. So you need 3 times as much grass seed to put grass on a square lawn because everything is tripled. So missing value problem. Even the numbers in problems often lead students to a cue on what they should do. This is a problem I already showed. The numbers look a bit different now, but if you see there's an integer ratio between the numbers in the problem. If you multiply 16 by 2, you end up with 32. So Kim has twice as many laps as Ellen. Or you could go the other way and say, later Kim has 3 times as much laps as in the beginning. Yeah. So that's the idea, integer ratios. But what if we make the numbers a bit harder? If we say Kim has around 24 laps and Ellen in the second instance has around 36 laps, now you have to multiply with numbers that aren't integers anymore. And we did a study to compare those 2 versions. And on the left, you see the integer version where they can easily multiply with easy numbers. And you again see that there's a decrease in the number of correct answers, an increase in the number of proportional answers, and quite a big number of proportional answers. But if we turn them to harder numbers, more difficult numbers, then you see that performance goes up. Of course, it still decreases with age, but performance, the number of correct answers, is much higher when you make the numbers harder. So students have a harder time to multiply, and they do it less often. In 4th grade, the proportional errors even disappeared completely. Okay. So things are avoidable, but they are not avoided in practice. And so there seems to be some work there for future teachers, for textbook developers, etc. So the consequence is that, well, this is one of the modeling cycles, so the problem-solving cycles that is used a lot in literature and word problem solving. There are others as well, but they always come down to students needing to understand a phenomenon that they investigate, then mathematize it, doing the mathematics, derive results from the mathematics, interpret them and report them. But the consequence of what we just saw is that students solve the problems in a very superficial way. So they skip the essential steps, and they think that most of the attention in word problem solving should go to the mathematical analysis, to doing the actual calculations, for example. And then immediately they report the results. And this, of course, is an undesirable practice, but it is what we see happening to some extent. Okay, I saw that there are some people in the audience who speak Greek. So a big disclaimer here, this problem is the runner problem that I just showed you before, translated in Greek by Google Translate. So probably it's a horrible translation. Nevertheless, this is the kind of problem that we gave to children in primary school in Flanders, in Belgium. So they speak Dutch, they don't understand Greek. But in a study, we gave this problem to children to say, hey, this problem is in Greek, but try to solve it anyway. And indeed, it seems that they don't really need to understand the problem, because quite many of them, you see, 20% of 5th graders, 39% of 6th graders give the proportional answer here. So they don't even need to know what's in the problem, they don't need to understand it, and they seem to have no problem in answering it. And they get a message based just on the numbers that are there. Okay, but again, this isn't a good enough explanation, we think, because it cannot explain. So the attention spent to proportionality and the way it is treated in education cannot explain why that overuse of proportionality is so persistent and resistant to help, and why errors happen much less often in real life. So we need a better explanation, or at least an additional one, which may be situated in the educational setting in which students are. So they are in a school setting, and that seems to affect their behavior. This is an example of what is given in a school setting. It's a textbook problem from a Portuguese textbook. I don't know if there are people speaking Portuguese here, but the problem isn't that difficult. Basically, it says that a washing machine takes 18 minutes to do 12 kilograms of laundry. How much time does it take to do 11 kilograms of laundry? And then you see the solution there being worked out, which is that there is a proportional relation between the kilograms of laundry in the machine and the time it takes. Now, there's a lot wrong with this problem. First of all, a washing machine takes way more than 18 minutes to do laundry. Even I know that, and I'm not doing a lot of laundry. And I also know that a washing machine doesn't take 12 kilograms of laundry. That's way too much. So it's completely unrealistic. But what is also quite unrealistic is that there is a linear relation between the amount of laundry you put in the machine and the time it takes. Well, and there's a disclaimer here, this problem is already about 10 years old. That's when somebody sent it to me. And at that time, washing machines took equally long, independent of the amount of laundry that was in them. But nowadays, washing machines can do this. So now there is a linear relation. If you put less laundry in, the machine will work shorter time. I don't know if it's a linear relation, but definitely when this was in the Portuguese textbook, it was completely unrealistic. Same here. I don't know if you know the Piaget's fish problem that was used to investigate proportional reasoning abilities in children. The problem was as follows. So there are 3 fish and there were eels. You can see them represented by a line here. The fish are 5, 10, and 15 centimeters in length. And Piaget then wrote, because there's only one dimension to be considered, fish B will eat twice the amount of fish A and fish C will eat 3 times that amount. Well, I don't know if that's the case, actually. Piaget was a biologist, and actually he should know that this relationship isn't necessarily linear in biological terms, but still he expected children to be unproblematic about this and just go for a linear solution. Okay, so what we're dealing with here is the activity of solving word problems in school. And children behave differently when they solve those problems in a school context versus in real life. So this is basically the situated cognition idea, which is a very prominent issue here at stake, of course. Other examples of research wherein we investigated word problems wherein children lacked what we call sense making have the same phenomenon. So children reason proportionally when they think that you sell 312 Christmas cards in December, that you will sell 3 times that amount in January, February, and March together, which is of course nonsense. People are late sending Christmas cards, but not that late. Or if you can run 100 meters in 17 seconds, probably it will not take you 170 seconds to run 1 kilometer, but many children will respond 170 seconds to the second problem you see there. Okay, so these are other examples. Now, with those examples that I've shown you here, where students lack a sense of reality when solving those problems, we investigated whether we could change that by involving humor in it. And so we developed little test booklets wherein we inserted jokes before they had to solve the problems that were on a previous slide. And you can read some of the jokes here on the slide. I'm not proud of them. They're horrible jokes, but for those children, they worked more or less. But these jokes typically involved some sense of reality. For instance, Calvin says, if I have 1 melon in one hand and 2 in the other, what do I have? And then the other one says, very large hands and strong muscles. So realistic reasoning on a mathematical problem. And these were jokes, and we had the children choosing between one or the other joke so that they would reason through those jokes. And then they received word problems that they shouldn't answer by means of proportions, but by means of reality. For instance, here the best time to swim 25 meters is 20 seconds. How long will it take somebody to swim 500 meters? Well, you can't say it's 20 times further, so the time is multiplied by 20. But that would be the unrealistic proportional reason. And we managed to show, and the reference is below, we managed to show that indeed, if you give those jokes before this kind of answers, students do better and reason more realistically than when you don't give those jokes. Okay. Talking about the sense of reality that students use or do not use when solving word problems, we also used this kind of word problems. Very simple ones where there isn't even mathematics involved. If you put 3 towels on a clothesline, after 12 hours they're dry, the neighbors have 6 towels on a clothesline. After how many hours are they dry? By the way, 12 hours is a Belgian situation because we have horrible weather. It does take 12 hours. But we hope children wouldn't reason it takes twice as much time for twice as many towels. And still, children do that. And look at the red bars. It's a massive, massive tendency. More than 80% of 5th graders answer that it takes 24 hours to dry the 6 towels. Now, the reason I'm giving this problem is that many people now suspect that the problem is, oh, but they're not reasoning through the problem. They're not taking into account reality at all. They just are using their reflex to multiply. But that's not really the case, because if we give the following problem in the same study, 5 musicians play a piece of music in 10 minutes, and now 35 musicians are going to play the same piece of music. How long will it take them? Well, if you use the same type of reasoning, you would say It's 7 times more musicians, so it will take 7 times more time. And yes, by looking at the red bars, you see that many children reason like that. Again, so it's quite worrying. But we saw a very sudden drop in 6th grade here. And that's what I want to draw your attention to. Look at the 6th graders that do this kind of reasoning much less. But we saw a lot of children here answering 1.4 minutes. And at first we were surprised by that answer, but it recurred quite frequently. So we said there must be an explanation. And we found out that the reasoning is most likely you're with 7 times as many musicians, so to do the same job, so it will go 7 times faster, because it's one job, but you're with more people to do the job, so you will be quicker. Now, the point I want to make is that if you look at the previous problem with the towels and this one, children are taking into account the context in some way. They are making sense of the word problem in some way. Both are wrong, but it's not like a reflex-like responding wherein they do not reason at all about the context. They do look at the context. Okay, a bit more time. I'll be shorter about the last groups of explanations, but still. As you probably noticed, we are going through time. The studies become more and more recent. There's no strict chronology, but still. In the last years, we have come to work a lot on the idea of intuitions in mathematics. I'll come to dual process theories in a minute as well, that you may be familiar with, because the way our mind functions is another layer of those explanations that we need to go into. And so we want to stress that students also tend to rely on their intuitions. So that's the first explanation. And then I will go into why that is quite normal in a mathematical classroom to do so. A basic idea that is quite dominant in a lot of our recent work, both in proportional reasoning, as well in our research in interpreting graphs, as in our research on rational number understanding, etc., is that human reasoning is led by what some people call heuristics, others call intuitions. These are insights that we gain almost immediately without being aware of it, so they're almost automatically, but we have those insights in an unconscious manner, while at the same time they're very convincing to us. We feel they are self-evident. And those intuitions are very often correct. That's also why we have them. In many situations, we immediately see a kind of solution, a kind of pattern, a principle, which is correct. But at the same time, it also seems to underlie quite deep-rooted errors. And a lot of this work has been done in the mathematics education community. Think of the work of Fishbein, or the work on the intuitive rules theory that has been done by research groups in Israel and elsewhere. More recently, the idea of dual process theories of reasoning. Think of Kahneman's work on thinking fast and slow, which is being applied in mathematics. Also, the research methods from cognitive psychologists are being applied in mathematical contexts nowadays. So it's that kind of research and theory. And we do see evidence in our research that that use of linearity is intuitive in nature, that there is an unconscious self-evident use of it. For instance, if we interview students about the enlargement of geometrical figures and what the impact is on area, then indeed you see that they very quickly go for a proportional method. It doesn't take them long to choose before they decide what to do, and once they do it, they're very quick in calculating. Second, they're very strongly convinced. If we start to question them and to show them other answers, they really are quite convinced of the correctness of their own answer, even when it is wrong. So they're persistent in it. And at the same time, they're almost not able to explain why that is the case, so why their solution would be a correct one and why others should be discarded. So that is first evidence. Okay. Other evidence comes from reaction time research, for instance. Here again, the word problem with the runners has been used. And now we put adults in front of a computer screen and we showed them solutions. Like here, very basic sentences to say to go from 5 to 15, you need to do plus 10. So you also have to do 30 plus 10, which is 40, which is a correct reasoning here. So students have to mark whether that is correct or incorrect. So they have to tick that it is correct. And we measure their reaction time to do so. And we compare it to similar problems, but now I changed the problem a little bit, saying they started together, but Kim runs faster, which turns it into a proportional problem. And now we give them the sentence that to say to go from 5 to 15, you need to do times 3. So you also have to do 30 times 3, and then see how quick they are in ticking that this is the correct reasoning. And it seems, that's what we found, that they're faster in finding out that this is the correct reasoning than when we showed them the additive problem and they have to take that this is the correct reasoning. So realizing that additive reasoning is needed seems to take more time than realizing that proportional reasoning is needed. And we did some other reaction time research, also research where we loaded working memory capacity. So these are techniques coming from that dual process theory area that have some assumptions to show that a certain type of reasoning is intuitive in nature and another type of reasoning is not. Okay. Then what I often have as a question when I present this work to teachers or to math education researchers is, well, our students shouldn't be doing intuitive reasoning in classroom. They are supposed to think analytically because mathematics classrooms are about real thinking and not about just superficial intuitive reasoning. Well, I don't necessarily agree, because if you look at textbooks, and I showed you examples already before, very often students will be successful if they use superficial approaches. If they look at the chapter title, they will often know what to do in certain problems. Or, besides correctness, often we value the speed with which a solution comes. And this is not something many teachers explicitly do. Very often they say, no, I prefer you to work a bit more slowly and come to the correct answer than to be too fast. That's true, but in classroom practice at the same time, you will often see that the teacher gives the students a bit of time to work on the problem, and then when some students have finished, it's time to wrap up and have a classroom discussion already. So some students haven't finished yet, but the classroom discussion, the collective feedback is already given. So implicitly, we are valuing speed sometimes. Okay, and we must be aware, definitely in the research, so the studies that we conducted ourselves, students are not always fully committed to the tasks they receive. Often they are not thrilled by the tasks, so they're not putting full mental effort in it. Sometimes they really can do better if they put full effort in it, but they often think that a superficial approach with little effort might be sufficient, and that's really the case. Okay, so you can say that a student who is doing intuitive processing is more adaptive to a classroom setting. And so in the whole dual process literature, there's a lot of debate on whether people are always rational, but Todd and Gigerens are saying, well, even if children are applying that intuitive reasoning in a classroom setting, that might be a kind of rational way of reasoning as well, but they call it an ecological rationality. Okay, a bit of time for the last, and here I want to go more into the developmental pathway towards proportional reasoning, and you will see that this is more recent work. A lot of it is just being reported or not being reported yet in the literature, so we are writing this up. And you will see, are a lot of my collaborators, and I saw in the team screen that some of them are attending the session. So I hope I give them sufficient credit by citing them. The main idea is in literature has been for a long time that multiplication is the most recent insight children get after addition. So multiplication develops after addition, and that's what we've thought for a long time. And that might be one of the explanations, but at the same time, and I will go into research in a minute, there seems to be some more potential in developing multiplicative reasoning in younger children already. Okay, so the traditional idea, and it's not a surprise, I think, that I'm citing Piaget here, is that multiplicative reasoning or proportional reasoning comes rather late. in the formal operational stage. And before that, children are only able to reason in terms of differences, which is additive reasoning. You see a more recent citation here that the transition from additive to multiplicative reasoning is a barrier, and it's a transition from one to the other. And that you will find a lot in the literature, definitely in older literature, think of 50s, 60s, 70s, 80s, but there is more recent literature that questions it. Here is some literature already from the 80s, 90s, by the way, that says that students are from a young age intuitively familiar with relations that apply in direct proportions, or that, yeah, if you use the right task, many children will already be able to show some indications of multiplicative reasoning. So maybe we are wrong to think that addition precedes multiplication. Okay. And some evidence that I want to bring out, but it is really preliminary, is that we are conducting a longitudinal study where we follow roughly 400 children. We started to follow them a few years ago when they were 4 years old, and we will follow them one more year until they are 9 years old in the coming school year. And we collected a lot of data on these children, a lot of background data, homeschooling, intelligence, numerosity capacities, language capacities, etc., but also some real mathematical measures involving estimation capacity, patterning understanding, probabilistic reasoning, and proportional reasoning. And that I want to go into. Here you see some example tasks that we used to measure children's proportional reasoning abilities. So we started giving children tasks like this from the age of 5, and these are just examples. We used a lot more variants of these tasks. For instance, there are 2 children, all children are equally hungry, and those 2 children get these 6 grapes. So if there's 1 child, how much does this child need to get so that it is fair? Or these grapes are discrete quantities. If we make it into continuous quantities, we say all children are equally hungry and this child gets this bar of chocolate. How much should we give to these 4 children so that it is fair? And then they should give a chocolate bar that is 4 times as long. And we're monitoring children's progress over the years. And one of the things I can report, but I'll tell you a bit more about other studies that we're doing, is that indeed from the age of 5 on, you start seeing meaningful responses. And by that, I'm not just saying that they're giving correct responses. Some children are giving correct responses at that young age already, but some others are trying to make sense of the problem situation in other more meaningful ways. So you start seeing first signs of one-to-many correspondence, for instance, which is already a good sign. So they have some mistakes there, but these mistakes are still meaningful, and we see these are precursors for proportional reasoning. And so these are described in the reference you see below. What we can also do is look at what predicts their abilities. And here is one study that we conducted wherein we found that language skills, the problem is a verbal one, so language skills really predict how children understand those problems and how well they do. And by language, we mean not just very general language skills, but also very domain-specific vocabulary. Words like half and twice as many and 3 times as many are crucial words, crucial expressions to understand the problem situations. And children's understanding of those specific expressions predict their development here. By the way, we also explored, and we're writing that up right now, how early patterning, so the skills of 4-year-olds to create patterns and to extend patterns, etc., is also predictive for their later performance in proportional reasoning. So these are all possible pathways. Okay, something more also quite recent, but more innovative, I think, if you look at the rest of the literature, is to look at the role of preference. Now, if you give this problem to children or to adults, and it's a very open and a bit strange problem to say, if I go from 4 to 12, and I do the same to go from 20 to the blank box, what should come in the blank box? Many adults will think 60 should be in the blank box because you multiply 4 by 3 to get 12, so you multiply 20 by 3 to get 60, which is perfectly okay. It's an option, it's a possibility. But many other people, especially younger children, we know by research, will say, no, to go from 4 to 12, you add 8. So you add 8 to 20, so 28 should be in the blank box. And there's an option, of course, for other things. Anything can happen. I mean, any relation could be there. Or you could say, well, it could be both a multiplication and an addition, etc. Now we are investigating using tasks like these and other tasks, whether children have a preference, which is kind of tendency to do the same pattern, the same kind of relationship all the time. And it seems that indeed many children are tending to multiply the whole time, others tend to add the whole time, and very few children realize that both possibilities are there. So we try to reveal that some children have more a preference towards multiplicative reasoning, others towards additive reasoning. And we found that it explains also their word problem solving behavior. So those with a multiplicative preference make more multiplicative mistakes, those with an additive preference make more additive mistakes, etc. Also, this can be done in younger children. If we use this problem where we have a magic hat, and if you put 1 pill in it, then 3 pills come out, and then we tell the children, if you put 2 pills in the magic hat, how many pills will come out? Now, there are many possibilities here, of course. You may think the hat adds 2 pills, and then you would say 4 pills come out. Or you may think the hat triples the number of pills, and then you would say 6 pills come out. Or you may think something else. It could be many things here, again. But it seems that children at the young age that we're investigating, which is 5-year-olds, 6-year-olds, 7-year-olds, do have a preference here. And we did find that this preference helps children in performing better on the proportional problems. And surprisingly, we even found that having an additive preference, which is what most children have if they have a preference, is helping them to develop their early proportional reasoning skills. Okay, so this is to wrap up. My time is almost up, I think. So we see that explanations for the kinds of mistakes are both situated in mathematics, in lacks in understanding the mathematical knowledge, but also the very concepts themselves are often linear in nature. But if we look at education, you can see that often some bad didactical choices are being made so that children can reason quite superficially in solving word problems. But that has to do also with the very situated setting of an education, of a classroom. But we also see that our mind tends to function in terms of intuitions, and that we often tend to have quick understandings of certain problem situations that may not always be the best ones. But again, this is something that we can expect to happen in a classroom or in a research setting where this is also at stake. And most recently, we are starting to look at the development of young children's multiplicative reasoning abilities. And we see that already at a young age, children can reason multiplicatively and not just additively. So the idea that multiplication is the more lately acquired concept that children met in classroom and that explains it is a bit questioned. Okay, now to come to concluding thoughts. This is something I want to stress, and this is more general and definitely not just limited to the topic that I took today, which is improper proportional reasoning. It follows more broadly, and this is something we've come to realize also more broadly in our research programs. And that is to adhere to single explanatory mechanisms, theoretical frameworks, or methodologies. I've shown you quite a range of methodologies, or to single paradigms is not sufficient to understand the mathematical thinking and learning, which is why larger research programs and collaborations across groups and disciplines is such a fascinating thing. And then, of course, well, I hope I convinced you that you can see errors as a kind of microcosm where a lot happens, a lot of explanations come together in a single error that children make, which helps us to understand mathematical thinking and learning. And so in order to understand that very well, you need to be very well aware of the mathematical concepts involved, so you need to be a mathematician, so to speak. You could be aware that historically the same mistakes have been made and mathematicians have struggled with the very same ideas that students struggle with nowadays. You have to be aware of what happens in the classroom, but also that the classroom is a very specific setting in which certain classroom norms, etc. hold. So having a sociological look at the classroom is already crucial as well, or having a sociological look at a research setting, because children behave differently when they're being researched than when they are not. This is also quite important. And looking at cognitive psychology, the fact that we rely on intuitions which have some cognitive psychological characteristics in terms of working memory, in terms of speed and so on, and a developmental psychologist. All of these roles have to come together in one single person if he wants to do good mathematics education research. And as I said already before, I'm not a mathematician, not a historian, not a teacher, not a sociologist, and not a cognitive developmental psychologist. Well, my time is up, and I want to thank you. I hope you could more or less follow this. I just wanted to throw in a last mistake that somebody tweeted quite a while ago, but I liked it so much. I made it anonymous, so the person involved is not shamed in public. Okay, I am open to questions. How are we going to run this? I see.
Thank you very much, Wim, to begin with. I think people could give you a virtual applause now if they wanted to, and then I'm very happy you're willing to answer some questions. I'm sure there will be questions. I see there's even someone who tries to join the meeting right now. Is that correct? That's a bit late.
It's 1 hour late.
Let's see. I'm checking the. Oh yes, Arthur has a very nice way to applause for you. You can see it in the chat.
Yeah.
For people who don't know, there's a way to raise your hand within Microsoft Teams. You just press the little hand that's at the bottom of your screen somewhere probably. And if I'm not responding to it and there's a silence, just feel free to switch on your microphone and start talking. But I'll try to. I see Harry Eikelhoff has raised his hand. Please go ahead, Harry.
I recognize the fact that students tend to reason proportionally. And you mentioned towards the end that language skills play a role. But I think it's not only the skills of language, it might also be that students try to avoid reading. And I understand quite well why students are doing better if you give them two alternatives, because then they're forced to read. And this is, I think, important in the discussion about the role of language in math education. If students are not willing to read, they try to go as quickly as possible to the answer, and then they tend to do proportional reasoning.
Yeah, that's I think something I understand very well, and you can say a lot of psychologists nowadays realize the importance of language in mathematics, and a lot of research has been done on, let's say, general language skills being related to mathematical performance and so well. But we also came to understand that it's much more specific, and that language, that mathematics requires a specific language and a specific preciseness of language. Many math educators, of course, know that, and most teachers know that as well, that preciseness of expression is crucial, and that students often lack that. They don't necessarily lack the skills, but then lack the habit of doing so, of expressing themselves clearly, of justifying themselves clearly, and so on, which is partly why we started that pathway to say, let's investigate if they understand, let's say, the vocabulary involved in proportional reasoning, but the same could hold for other topics, of course. And I know this is kicking an open door for many math educators who know the importance of it. But if you look at the psychologists we work with, very often they think of language as something very general, etc. So yeah, I do agree. And in research, by offering the multiple choice, They should be more careful in reading, definitely. That might help, but for research purposes, giving multiple choice questions is also not always desirable, because you're eliciting a kind of thinking that, yeah, you don't necessarily want. It may affect your results in an undesired way, etc. Yeah. You want to go into that further?
Thank you. No, thank you.
Yeah. I see Paul has raised his hand.
Yes, thanks for your very nice talk, Wim. And I have a question. There was a few slides back. You had this quite surprising comment about predictive, about additional preference, predicting proportional reasoning or something. Yeah, this one.
Yeah.
It sounds so. How do you explain this? Maybe I missed it, but that was not clear to me.
It's true, I didn't explain it. So this is it's my way of triggering questions that I want to answer. Now, how to explain that? We measured the preference of children at an early age, 5 years old, roughly speaking, for 5 to 6 years old. And what we noticed is, first of all, very few children do that preference task multiplicatively. We had also other preference tasks, by the way. So you don't see a lot of multiplicative preferences yet. Now, those few children who had a clear multiplicative approach already did, of course, also better on the proportional problems. That to be clear, but they're very few. But we noticed that also those with an additive preference do better than those children where we could not say they had a preference. So those children who gave, roughly saying, random answers to the preference task. It's probably not random, by the way, but who didn't give the expected 4 pills as an answer here, but did something else, maybe the whole box of pills, or just said 2 pills. So there are a lot of children who give we say non-relational answers, who don't show a clear preference yet. And maybe there the explanation is situated, because you could say these children are not paying attention to the mathematical characteristics of the problem at all. They're just saying, give some number of pills, the whole box, or they're not noticing that the number increases, so they're not giving an increased number, but just 2 pills again. So those with an additive preference, you can say they already paid attention to the fact that there is a mathematical relationship here. And that already seems to be a good thing, because they pay attention to something that is relevant also in proportional reasoning tasks.
But if I may ask, then your explanation that you give now makes sense to me, but it is not saying anything about the order of addition and multiplication, or addition and proportion, which I thought you suggested. You said then the order is questionable.
Yeah.
But now your answer now seems to be like, if they have an early additive preference, it means that they capture the mathematical idea of addition, which is kind of predictor for later proportional skills.
I must confess, well, we're struggling with this. We try to understand. What I do want to state, and I think we can justify that, is that addition is not necessarily preceding multiplication, but that both might be there at the same time. And now in this preference task, children may solve the preference task additively, but this is not saying that they cannot solve it multiplicatively. It's their choice to do it additively, which is fine, but it just shows what they choose. They might be able to do it proportionally, actually, so multiplicatively. But I think the point I want to make is, well, we see, and that's more with the ability, so the right side of the screen, these are tasks where you can say these are proportional. You cannot judge them as additive, they are proportional. And also at that young age, some children are able to do that already quite well. So even there, they are able to reason in some way multiplicatively, not the full thing, of course. So it is present in that age already in some children. So I don't think there's a real order in it. It seems to be something artificial in the tasks we use and in the education we use. We start by adding, not by multiplying. by counting, by the way. So our idea of in education is that we first teach them the numbers and counting rather than quantities, which is a multiplicative idea, by the way. And you could start by doing that as well instead of counting. It's a broad thing now. I mean, I generalized quite a bit, I know. It is definitely something we are going to struggle with for a long time in the coming years to investigate this further.
Thank you.
Yeah. Others? Anna is raising a hand.
I think Lonneke has a very good question in the chat.
Yeah, but I wanted to say somehow I'm an outsider in Teams. We don't have Teams in our organization, so I can't read the chat. I tried, but it's only available to team members, it says.
Yeah, so, Lonneke, maybe then you can speak it out.
Yeah, what I was wondering, Wim, given the results of this line of 20 years of research, what kind of advice do you have for teachers? And I got some advices from your presentation already. So I wrote that you advise us to give jokes to students that make them think before they start doing real-life problems, mixed problems, so they have to think about the solution strategy and not give them all additive or all proportional or multiplicative problems. Mm-hmm. Maybe check their preference, maybe check if they already can do something with patterns.
Yeah.
So what are the advices you gave?
Well, you already gave quite a few, I think. First of all, many of them we need to check causally. We need to check whether, now we saw a correlation between early patterning skills, for instance, and later proportional reasoning. But that's a correlation. Even if it's longitudinal in time, it's still correlation. But of course, we can see now if we start intervening and teach patterns in 4-year-olds, how they do proportional reasoning when they come in primary school. So all of that is still, I mean, with some caution. But yeah, you mentioned quite a few things already. And there's a lot to gain in a very short terms if you look at textbook materials. Because a lot of the textbook materials allow quite superficial approaches. It's very often just long series of exercises requiring the same approach, and rarely or even none of the time they need to look and distinguish problems from each other. So that is something that I think the quick gains are over there. If you want to do things more drastically, I think yeah, there's no necessary need, I think, to start by addition and teach multiplication later on. I think both could do, well, they could be reversed, but that's quite drastic. And then you go into some Russian researchers, by the way, have tried these things, I think, where you start from the idea of quantity and measurement, which is a multiplicative idea. So you have a quantity and something else that you call the unit, and you construct a number concept based on that, rather than on the additive idea of I have none, and then I add one, and then I have one, I add another, I have two, which is additive reasoning. You could reverse it and start with multiplicative ideas from the start on. That's very drastic. Or I think, and that's the middle way, to introduce multiplication a bit earlier and spread out the whole sequence of both types of operations throughout education, rather than start with one and then with the other. So, but these are definitely not quick gains, and they're really complex. Yeah. I think there are many more that you also referred to, by the way, already. I think you picked out the ones that I had in mind. But I'm typically, yeah, I want to be cautious because we don't do that much intervention research. By the way, we are going to do intervention research in proportional reasoning in 2nd grade. So we will teach 2nd graders to solve the problems that I showed you, but even more advanced ones. Also for probability, by the way, we're going to teach probability in 2nd grade, which is a challenge, but we'll see what comes out. And then I will be more confident on what to do in practice. So far, give us some more time.
And if I am allowed one more question for this, do you also have advices for secondary schools education?
We did quite some research also in secondary education where the same problems keep coming back, but they come back in a different shape, so to say. At that point, there is some point in secondary education where students learn about linear functions, and linear functions in terms of y equals ax, but then also y equals ax plus b, where there's a constant like an intercept, there's inverse proportionality, etc. They have a function, they have a table, they have a graph, so the function formula, I should say, and the link between those is also not straightforward. And students learn to reason about properties of functions. They're never doing calculus and saying, for instance, in some cases, if x doubles, y doubles, x halves, y halves, etc. These are properties of linear functions. They do not hold all for other functions. Some do, or some are a bit more subtle and so on. And going explicitly into that is, again, deepening the understanding of the things I talked about here today. So definitely in secondary education, it translates into calculus, but also the link with physics, physical contexts. There are a lot of linear contexts in physics, but also a lot of non-linear contexts in physics. And so this can easily be expanded, I think, to that kind of topics where the same mistakes, by the way, occur. In probability, in physics, in chemistry, and so on. We see problems like that. We see that students struggle with translating from a formula to a graph. What graph belongs to which formula? If they look at a table, what's the relation between the columns in the table? What's the relation between the cells if you go down, etc. is really difficult for them. And it is because they don't have a clear understanding of, they don't have a meta view, so to say, over the range of functions they can handle.
Thank you.
Do you have additional ones, Lonneke?
No. I leave the floor to Anna.
Okay. We can't hear you. Your mic is muted. Anna? Yes.
Yes. Okay. Thanks. Yes, I think Lonneke bumped you with the most difficult question ever, and we must also speak for practice something. And Alkan is the one who also raised the hand.
Okay. Yeah.
Please come in. Sinem Alkan, I don't know who is it, but.
Oh, hi, this is Konstantinos Xenofondos. I asked my colleague Sinem to raise her hand on my behalf because it seems that I have an older version of Teams and it doesn't give me the option. Well, I have a question about the examples you showed with that could be solved either with an additive or multiplicative reasoning. And I was wondering, because you talked about, yes, those examples, you talked about children's preferences towards either additive or multiplicative. And I was wondering whether if you have given a third pair of values to children, in which case the problem would be only additive or only multiplicative, whether those with an additive preference would still use their preference, or those with multiplicative will still use their multiplicative preference.
Well, we thought about that. That's a very nice idea. So instead of, for instance, offering a word problem where there is one solution only that is correct, and the other one is the wrong model, you could do that as well by showing them multiple arrows, of which some of them are filled in, but one is not. We haven't done it. I think that might be a good idea. It's definitely a possibility. I think some others in the past have done something along that line. And yes, you will see that then indeed they start making the mistake again as well. Because they often quickly see, apparently many people immediately see a ×3 here on the screen. Well, of course, that is an automatized thing, and we learn the multiplication table, so we don't think any further. As soon as that has crossed our mind, this is the only thing we think of, and it seems to take some effort just to refrain from that and to say, yeah, but wait, there are other possibilities here as well. Yeah, so good idea, I think. If other options, if other people want to start a research on that, feel free, and we're happy to collaborate and give you advice or so. For sure.
Okay, thanks. If there is no more question, I perhaps like to ask one, and that's a little bit on the level of the meta message that you sent, that you gave us, that there are different lenses and each one provides a kind of answer. And I was thinking, like, also coming back to your idea that, for example, the Davidov, a Russian psychologist who were trying to teach multiplicativity and additive strategy, not in a sequential order, he was speaking about starting not from numbers, but from actions. Yeah. And thus, I think that he was speaking from starting of development of intuitions, rather than just operation and analytical thinking. So I was wondering if you consider that your, so to speak, psychological lens and developmental and even sociological lens in terms of which curriculum is approached are actually kind of converge into this issue, what kind of intuitions we develop and what kind of automatic strategies students are prompt to.
That is the hardest question I could get, I think, not the other one. No, I think, yeah, you say these perspectives could converge at some point. And I think indeed, if you look at the Davidov work, that is what is exactly happening. So they start from actions, and at some point, of course, yeah, concepts develop, so to say, from actions, and the concepts are intuitive in nature, so to say, you're building intuitions. And I think that is very valuable and very reasonable to say that we're building intuitions, but then the right intuitions. Because I spoke today, I think, a bit negative about intuitions, and a bit inherent to that work on intuitions, definitely from the dual process perspective, is that we are looking at when intuitions lead us the wrong way. That's what we typically do in research, but that's most often to show their presence, because you can show it by showing that people make mistakes. But most often, intuitions are a good thing. And definitely, if you start from that Davidov idea to say, okay, you see quantities and you handle quantities, you compare them. Maybe at some point you want to feel the need to measure them by adding quantities or by comparing them in other ways. Yeah, you can build up the idea of number in that way, which is I think much more valuable intuition of what a number is than the additive idea, which is a discrete number and you always add 1 to obtain the next number, which leads to all kinds of mistakes. A lot of people have done research on rational number understanding, where people make mistakes, for instance, thinking that numbers are discrete and that there are only a few numbers between 2 other numbers. All of that is inherent to the additive idea of a number. While if you see a number as a ratio, that's a rational number, yeah, you avoid that already. So if the intuition of the number is set right at the beginning in kindergarten, you might be able to avoid that. And then the intuition is a more valuable one. It prepares for later learning, you can say. So I think it's a good suggestion.
So that's actually very interesting what you say. You say now not that we need to overcome intuitions, but rather that we need to build diverse intuitions and flexibility of choice of intuition, which also doesn't necessarily need to be analytical, this choice of intuitions, right? Yeah. Right? We kind of bump on perceiving a problem for a particular side.
Yeah. It's also something tempting to say, oh, we need to overcome intuitions. And this is, I've heard Daniel Kahneman speak about that as well. It's the question he gets most of the time. This is the idea of thinking fast and slow. So it's a very popular type of research and literature. And so he wrote some popularizing books on that. It's always about how do we overcome the intuitions? Well, a cognitive psychologist typically will say, you can't. Forget it. I mean, our brain does not function like, oh, there's an intuition that I need to overcome. Unavoidably, we will have intuitions. We keep having them. We need to be aware of them, but still they will pop up now and then. An example is, well, very simple ideas like fraction comparisons, comparing fractions. Many children will think that if the numbers in the fraction are larger, the fraction is larger. Well, okay, adults make those mistakes not anymore typically, but we found that even mathematicians show longer reaction times on fraction comparisons where that intuition is at play. So even they're not escaping the intuition. They have it in terms of reaction time and so on. And what's inherent in that idea of intuition is that it will pop up now and then if we're not paying attention, or if we are distracted, or if our working memory, psychologically speaking, is loaded with other things already. So if there is noise, if we need to keep another result in mind, our intuitions will pop up again. And if they're wrong, yeah, we will make a mistake even if we know the right answer. And that's why indeed you can just say, like, make them our friends, not our enemies, these intuitions. Set them right from the beginning. And if we can make the intuition of a number set very early in a good way, that would be nice. That's not to say that we won't make mistakes anymore. They will come back. But okay, let's live with that.
Yes.
Yeah.
Yes, something like this. Yes, from embodied cognitive science perspective, I would say intuitions, that's what we are built from. And
yeah.
Finally, our reason is made from intuitions. I'm looking for more questions. I see there was a small conversation between Arthur and Paul. Is it something you would like to bring?
I can't read the chat.
Yeah.
I'm an outsider, so
I'm asking them
to do it
to
behind my
speak.
back. Feel free.
I just liked very much, Wim, your point of comparing different approaches and speak explicitly about them. And so this discrimination training, and Arthur said most chapters deal with one topic. And of course, you have these famous examples, like after solving a lot of quadratic equations, many students will think that the equation like 5 squared times x equals 50 will be a quadratic equation. So I just wanted to underpin what you're saying.
Yeah, it is. And again, this is tempting, and it's part of the school grammar to do that because repetition is important. We can't escape automatization and so on. But the risk is that we forget that there's more going on. And
exactly.
Yeah. By the way, if you would be aware of textbooks or classroom materials that do this well, I'm very happy to see it. If you could scan it or send me references to it and so on, because it's extremely rare, and I would really love to see somewhere in the world this being used so that we can do research there to see if it works, how it compares to performance in classroom where it doesn't happen, for instance.
I actually would invite you to try maybe investigate something in Russia, because there are so many word problems in the textbooks, and there are certainly in mixed order.
Okay.
I might maybe send you some pictures of the textbooks that you to underpin it, but I thought that could be interesting. Like just a personal example, my son coming now to the Netherlands is really shocked by the level of word problems, because he says again and again they put me first grade word problem, and so that's probably, if you want these things, that could be interesting.
And at that point I will need collaboration, because like Greek word problems, Russian word problems are typically very hard. German, French, English would work, but Russian.
But maybe let's I will think about it. I have some colleagues for whom it could really ring a bell. That's really that could be interesting, because that could be really different environment.
Okay, but very nice idea.
You see in the chat. I will drop chat to you at the end, because there are more suggestions of different Netherlands textbooks now who do this, like Mathflows and Magnesium method. So maybe you don't need to go that far.
And I can even understand that. There may be some cultural issues, but Okay, if you could copy it, because I don't have access. It's quite annoying. Teams.
Yeah, it's a pity. We should take
okay.
mind. Yeah. Yes. Okay. I think we have time for maybe one more question before we'll. Yeah. Okay. I actually have one. If there is nobody else, and I think that's quite interesting. I was thinking of the role of materiality, how I think of it from a embodied perspective, but in a very particular way in your case, I think that a lot of proportions we learn like 4 numbers, 1 under 1, 1 under 1, right? And this is a very strong visual pattern. And in quite a few problems that you have been showing to us, this actually maintained. So it's kind of visually provoke the use of proportional. Have you been trying to avoid it, to investigate the impact of this exactly visual special?
We haven't explicitly investigated it. I think, yeah, you're right. It may trigger it as well. Now, I must say, I intentionally put word problems on the slide that would allow that you see that force structure, because I thought for didactical reasons today it should be very clear. I gave a lot of information in a short time so that you at first sight should see the structure of a word problem, that it would help you. In many cases, when it appears in the text book, in the test booklet for children, it's not that straightforward. We didn't underline the numbers, we didn't highlight them, etc. That was for you now. But still, very often, I think in the end, you would see that force structure there. And it might be that if you avoid that, that things go better, definitely, yeah. We try to change the wordings a bit, so to avoid the missing value formulation, and then students do better, actually, yeah. So again, avoiding it. If you have a suggestion on how to do it, because I don't immediately see how I could possibly do it.
Yeah. Even formulating one of the numbers like in another word that could.
Yeah, okay, yeah. Maybe that's already a trigger less, actually. Yeah, that's a good idea. Yeah. Okay, yeah, that's a good suggestion.
Something like this. Yes.
So
okay.
Usually we end up with more work and more new research plans after the seminar. Thank you for that.
And that's maybe a valuable outcome, because I thank you very much, Wim. I think that was a very exciting presentation. I don't know how everybody, but at least I have highlighted some methodological tricks that I might use later in my research. Okay. So that's very valuable. And that's, I think, was good that we have conducted this even online method education seminar.
Yeah.
I don't know how should we applaud to Wim, but I can do it with my mic. Great.
It's a pleasure. It was fun to do. It would be more fun in real life, but still, it was very nice. Thanks for the invitation. That was really nice. So maybe we should follow up, and if you're still doing it online, we might come also in the next seminar, because I see a lot of outsiders actually, so that's good.
You're welcome.
Okay. Maybe we should announce our next seminar, which will take place in September. After the summer, I think we'll have a little summer break, and I like your idea of doing this online, and I think at least also a mixed form should be possible to increase the audience, where if in the Netherlands we once we'll be able to do this in a live setting, we should do it in a mixed form so that it's also online at the same time.
But Rogier, wouldn't the procedure be that if you want to be on the mailing list, please send your email address to Anna or Rogier?
Yeah.
Yes, or you could even subscribe to our email list directly through our website, and there's a button you can click or a link you can click to subscribe yourself, but email us is fine too, yes.
Okay, very good. So have a nice day.
I think that's all we're going to say, yes, and we'll go.
Nice
Thank
day.
you for attending, everyone, and I hope to see you in the future.
Yeah,
version
we
of
will
this
send
after the
information
summer.
soon.
Okay, good.
Thank you.
Bye
Wim.
bye.
Very
Bye.
much.
Thanks.
Bye-bye.
Bye.
Bye.
Привет. Привет. Привет.